I want you to picture something for a second. You are sitting on your couch, you've got a controller in your hand, or maybe you're sitting in a dark movie theater with a huge bucket of popcorn.
Yeah.
You are looking at a screen, and on that screen is this photorealistic ocean.
Oh, yeah, the classic water simulation.
Right. You can see the waves cresting. You can see the sun catching the ripples, scattering light into a million tiny blinding glints. You can see the dark, murky depths underneath, and maybe like the distorted reflection of a cloud passing overhead. It looks wet.
It looks undeniably real.
Exactly. But here's the thing. You are looking at a completely flat piece of plastic and glass, illuminated by a grid of tiny square pixels. How does a flat screen of pixels trick the human brain into seeing wet, reflective, dynamic light?
I mean, it is the ultimate illusion, isn't it? At its core, that display is doing nothing but firing binary instructions. It's just ones and zeros pushing voltage through liquid crystals or organic LEDs.
Right.
Yet it translates into this incredibly visceral physical experience. We are so used to it now that we totally take it for granted. But the leap from a flat grid of colored squares to a simulated, breathing reality is, well, it's arguably one of the most fascinating translations of physics into mathematics in human history.
And uncovering how that translation actually works is the mission of this deep dive. We are going to look under the hood of digital reality to explore the mathematical engine that makes that photorealistic ocean possible. It's a concept called ray tracing.
Yes, the holy grail of computer graphics.
Totally. And to figure this out, we are diving into some absolute masterclass material. Specifically, we've got the architectural blueprints of rendering engines taught by Professor Slusalek at Saarland University. I have been poring over this curriculum, and I feel like I've just been handed the secret source code to the universe.
It really fundamentally changes how you look at a digital image, because we are going to explore not just how to draw a picture, but how to actually simulate the physical behavior of light itself.
Which is wild to think about.
Right. We are not just digitally painting. We are taking the fundamental laws of thermodynamics and optics, like how photons travel, how they bounce off varied surfaces, how they lose energy over distance, and we are meticulously translating those physical laws into logic gates and lines of code.
But before we can simulate light bouncing around, we have to actually build the universe that the light is going to bounce around in.
Yeah.
You can't have a reflection without a mirror.
Exactly.
And you can't have a shadow of an object to cast it. We need a digital film set.
Yeah, in computer graphics, we refer to this as assembling the scene ingredients. We are essentially playing the role of a digital architect, right? Constructing a three-dimensional universe entirely from scratch.
Okay, so where do we start?
Well, this universe exists in MathBR3, the three-dimensional mathematical space, meaning everything inside it must be defined by numerical coordinates along an x, y, and z axis.
Let's furnish this universe then. If this is a film set, we need our actors, our props, our wardrobe, and our camera. Let's start with the physical stuff. The curriculum defines these as shapes, but we aren't just dropping in like fully formed humans or cars right away.
No, you have to start with primitives. Primitives are the fundamental atomic building blocks of any 3D environment. Think of perfect mathematical spheres, boxes, cones, cylinders, and triangles.
Triangles seem almost too basic, though.
A simple flat triangle might seem too rudimentary to be useful, yeah. But if you stitch thousands or millions of them together, you can approximate almost any complex organic surface, from a jagged mountain range to a human face.
But the material gets into shapes that are much more complex than just folding a bunch of triangles together like digital origami. There's a whole section on implicit functions. This is where it started getting a little abstract.
Oh, implicit functions are brilliant.
Yeah, because instead of storing a shape as a list of flat surfaces, a quadric is defined purely by a mathematical equation. It's a surface where every point satisfies a specific formula, like a perfectly infinite cylinder or a sweeping paraboloid.
Right. It is a pure mathematical curve floating in the void. That is a crucial distinction, because a triangle mesh is explicit. The computer knows exactly where the corners are.
Okay.
But an implicit function is more like a rule. The computer doesn't store the shape itself. It just stores the mathematical rule that defines the boundary of the shape.
So how does it draw it?
Well, when we get to the process of shooting light at it, the computer essentially asks the equation, did my light ray satisfy your rule? If yes, it hit the surface. This allows for mathematically perfect curves that never get blocky or pixelated no matter how close you zoom in.
That makes sense. Then there are Boolean operations, which I find incredibly clever. This is called constructive solid geometry.
Oh, yes. CSG.
Let's say I want to model a coffee mug. Instead of trying to bend flat triangles into a cup shape, I could just take a solid mathematical cylinder. Then I take a slightly smaller cylinder, place it inside the first one, and tell the computer to just subtract the second shape from the first.
You're carving with math.
Exactly. It literally scoops out the negative space, leaving a perfect cup.
Yeah, you are combining, intersecting, or carving shapes using pure logic. It is digital sculpting. But a shape, whether it's a billion triangle mesh, an implicit equation, or a Boolean carved block, it's just naked geometry.
Right. It's invisible.
Entirely invisible until it interacts with light. And that brings us to your wardrobe and makeup analogy, materials. We have to explicitly define the light reflectance and emission properties of every single microscopic point on those objects.
This is where we tell a computer what things are actually made of. We have specific functions for diffuse versus specular reflection. Diffuse is your matte finish. It's a brick wall, a piece of paper, or, a piece of chalk. When light hits it, it absorbs some energy and scatters the rest in every possible direction evenly.
While specular is your shiny highlight.
Right. It's a polished bowling ball, a freshly waxed car, or like a wet eyeball.
And the combination of those two properties dictates almost everything about how we perceive an object's texture. But we don't just assign a single property to a whole object. We map textures onto them.
Like wallpaper.
Exactly. Two-dimensional images wrapped around the three-dimensional geometry, or even more powerfully, we use procedural noise functions.
Right, like Perlin noise. I was reading about this. Instead of using a photograph of wood grain, which might repeat or look blurry if you stretch it too far, you use a mathematical algorithm.
Because a photo has a set resolution.
Exactly. But the algorithm generates a chaotic but structured pattern that mimics nature perfectly. You can generate infinite, non-repeating marble or cloud patterns just mathematically.
We also define the rules of transparency. Like, is the object solid? Is it a piece of frosted glass that scatters light as it passes through? Or is it a body of water that bends the light according to an index of refraction? Every single optical property must be quantified into a variable.
The sources even dive into advanced objects that aren't solid shapes at all. Things like volumes, smoke, fog, fire.
Yes, volumetric rendering is a whole other beast.
And point clouds, which are millions of individual data points hovering in space, usually gathered by LiDAR scanners mapping real-world environments.
So, okay, we have built this incredibly dense, mathematically defined room. We have our shapes, they're wearing their materials, they have texture. Now we need the camera to capture it all.
The camera is our virtual eye into the Math 3 space. But unlike a physical camera, which is constrained by real lenses and glass, our digital camera is just a point in space defined by variables.
So what are those variables? Well, first we decide the projection type. Is it a standard perspective camera, which mimics human vision, where parallel lines converge in the distance and objects get smaller as they move away?
Right, the way we normally see the world.
Exactly. Or is it an orthographic camera, where those perspective rules are thrown out? That's often used in architectural rendering or engineering because it preserves parallel lines and exact scale regardless of distance.
Or a fisheye lens that aggressively distorts the field of view. And we have to give this camera its stage directions. It needs an origin like its exact XYZ coordinates in the world.
Yes, where it is standing.
And it needs a direction vector.
Okay.
Exactly where it is pointing. And it needs a field of view determining how wide its peripheral vision is. Okay, the set is built, the camera's rolling. But before we start shooting light around, we have to talk about the physics assumptions.
Ah, yes. The rules of the game.
Because the rendering engine plays by a very specific set of rules, and I mean, some of them are huge cheats.
They're absolutely cheats, but completely necessary ones. Simulating the entirety of physical reality is a computational impossibility. There isn't a supercomputer on Earth that can simulate every atom and photon in a single room down to the subatomic level.
Right.
So the rendering engine sets boundaries to keep the mathematics solvable within a human lifetime.
The first major assumption is that light only reflects off surfaces and objects. Empty space is treated as a perfect, frictionless vacuum.
Which is completely false in reality.
Yeah. In the real world, if I shine a flashlight, the light is actually hitting millions of dust particles and air molecules, scattering slightly. That's why you can see a laser beam in a smoky room. But the computer assumes the air is literally nothing unless we explicitly program a volume of smoke.
Correct.
But the part of the curriculum that really stopped me was the explicit instruction. No quantum effects, no relativistic effects.
Yeah.
We are playing God in this digital universe, but we are explicitly locking Einstein and quantum mechanics out of the building. Why do we intentionally dumb down the physics?
Well, it comes down to understanding the true objective of the simulation. The goal of a rendering engine is not to act as a scientific sandbox to uncover the fundamental truths of the cosmos. The goal is to fool the human visual cortex.
So we only simulate what we can actually see.
Exactly. We only simulate the physics necessary for a human eye to perceive an image as real. Quantum superposition doesn't change how a human perceives the color of an apple sitting on a wooden table.
Right, because my eye can't see a photon acting as both a wave and a particle simultaneously. The computer doesn't bother doing the math for it.
Precisely. And relativistic effects like gravity physically bending the path of light around a massive object are totally irrelevant unless you are specifically rendering a scientifically accurate black hole.
Like an interstellar.
Exactly like that. We ignore the subatomic and the cosmic to save our computational budget for the macro scale, the scale humans actually experience.
It is a brilliant, practical compromise. So our rules are locked in. We only care about everyday physics. Now comes the biggest problem. How do we actually capture this massive three-dimensional universe and flatten it onto our two-dimensional television screen?
The million-dollar question.
The material presents two entirely different philosophical approaches to this problem: rasterization and ray tracing.
Yeah.
Let's start with rasterization, because for decades, this was the absolute undisputed king of video games and real-time graphics. If I played a 3D game in the 90s, 2000s, or even the 2010s, I was looking at rasterization.
Yes, absolutely. Standards like OpenGL and DirectX were entirely built around this paradigm. Rasterization is what we call an imperative object-centric process.
Okay, what does that mean practically?
It is fundamentally about drawing the scene from the perspective of the camera, object by object. It takes your 3D geometry, calculates where those objects sit relative to your 2D screen, squashes them flat onto that 2D plane, and then simply colors in the pixels that fall inside those flattened shapes.
I always picture it like taking a complex 3D wireframe model, shining a massive flashlight behind it, and tracing the shadow it casts onto a flat wall. You are projecting whole objects at once.
That's a great visualization.
And because you are just doing a geometry trick to squash them flat, it is unbelievably fast. That speed is why it literally built the gaming industry.
The speed is unmatched, yeah. Because the hardware is essentially just moving triangles and coloring inside the lines. But rasterization has a massive fundamental flaw. It is completely blind to how light actually works.
It doesn't simulate light at all.
No. It essentially fakes reality through a series of incredibly clever but ultimately fragile hacks.
Oh, wait, if I'm playing a game from 2015 and I see a reflection in a puddle or a shadow cast by a building, that's not a real shadow. How does rasterization fake that?
Well, because rasterization processes objects one by one and projects them onto the screen, it struggles immensely with anything that requires objects to interact with each other optically. Let's take a mirror. If you want a mirror in a rasterized scene, you can't just assign a reflective material to a flat plane and expect it to work, because the engine doesn't bounce light. It has no concept of a bounce.
So how did they do mirrors in older games?
To fake it, developers often had to literally duplicate the entire 3D room, flip it upside down, and place it underneath a transparent floor. When you looked at the mirror, you were actually just looking through a glass floor at a second upside-down room.
That is hilarious. It's a digital magic trick.
Yeah.
Smoke and mirrors, quite literally. What about shadows?
Shadows require another hack called shadow mapping. The engine has to pause rendering from the player's camera, fly a second invisible camera over to the light bulb, render the entire scene from the perspective of the light, record which surfaces the light can see and which are hidden, save that as a black and white texture map, go back to the player's camera and project that dark texture onto the ground.
That sounds exhausting and incredibly prone to breaking. I mean, if I want a glass sphere reflecting a mirror that is reflecting another glass sphere, rasterization just throws its hands up.
It completely collapses, yes.
Which brings us to the hero of our exploration: ray tracing.
Ray tracing abandons all the clever hacks. Instead of projecting shapes onto a screen, it is a physically based simulation of light transport. It actually models the actual paths of light bouncing through the environment.
Wow.
Because of this, it inherently supports deep recursion.
I mean, effects like realistic shadows, reflections, and the bending of light through glass aren't faked. They happen naturally out of the box because that is simply how light behaves in the simulation.
Exactly.
But the cost is immense. The material warns that ray tracing is incredibly slow if you don't build it brilliantly. And this leads to what I think is the most mind-blowing comparison in the entire curriculum: The performance scaling between the two.
Yes, we are talking about algorithmic complexity, often described using big O notation. This describes how an algorithm's required processing time grows as the amount of data grows.
Right, like how it scales.
In rasterization, the scaling is linear, which is linear.
Okay.
The number represents the number of objects or triangles in your scene.
So if I have a simple scene with 100 triangles, it processes fast. If I double the scene to 200 triangles, it takes roughly twice as long, because the graphics card has to grab every single new triangle, check where it is, and project it onto the screen.
Precisely. It is a linear relationship. Now, consider a modern digital environment. Imagine a dense forest. You aren't rendering 100 triangles. You are rendering 10 billion individual pine needles, millions of leaves, bark textures, rocks.
A huge amount of geometry.
If you try to rasterize that, the linear scaling becomes a bottleneck. The system chokes because it has to process every single one of those billions of triangles to see if they end up on the screen.
But ray tracing scales completely differently. The material states it has operand monoscalability, logarithmic scaling. If I remember my math classes, logarithmic scaling is incredibly powerful when dealing with massive numbers. Why does ray tracing scale so much better?
It is the secret weapon of the architecture. Ray tracing is heavier per pixel, sure, but it doesn't loop through every object to draw the scene. Instead, it organizes the 3D scene into highly optimized spatial data structures. The most common is a bounding volume hierarchy, or a BVH tree.
How does that work in practice? Let's use the forest example.
Okay. When a ray of light flies through the scene, it doesn't check itself against all 10 billion pine needles. The engine has pre-grouped the forest. It draws a giant invisible box around the left half of the forest and another box around the right half.
Okay.
The ray first asks, did I hit the left box or the right box? It hits the left. It instantly ignores the 5 billion needles on the right.
It completely throws out half the math in a single calculation.
Exactly. Then, inside the left box, there are smaller boxes, maybe one for the top of the canopy and one for the ground. Did I hit the canopy or the ground? The canopy. It discards the ground. It recursively narrows down the search space, stepping down through the branches of this mathematical tree until it finds the specific leaf the ray intersected.
It is essentially playing a game of 20 questions with the geometry.
That is the perfect analogy. And mathematically, a game of 20 questions allows you to pick one specific item out of over 1 million possibilities. 2 to the power of 20. If you add 1 billion more pine needles to the scene, you don't add 1 billion more calculations. You might only need to ask 1 or 2 more questions in your tree search to find the right intersection.
That is astounding. The material describes it as output-sensitive and demand-driven. You only calculate the light paths that actually matter to the camera's pixels, completely ignoring the billions of complex objects hiding behind the camera or locked inside a building where no one can even see them. It is working smarter, not just harder.
And while the silicon hardware capable of doing this in real time is an invention of the last few years, the conceptual framework of tracing a ray of light is actually ancient.
Oh, I was absolutely fascinated by the historical context provided here. The idea traces back to Empedocles, a Greek philosopher living around 450 BC.
Yeah, that was wild to read.
He theorized that the human eye actually emitted rays of invisible fire that reached out and illuminated the world around us.
Which, from a physics standpoint, Empedocles was completely backward. But from a computational standpoint, as we are about to see, his theory of vision is exactly how modern rendering engines operate.
It's beautiful irony. And it didn't stop in ancient Greece. The curriculum highlights Albrecht Dürer, a Renaissance artist working in 1525. There is this incredible woodcut image showing his physical setup. He wanted to draw a lute, a stringed instrument, in mathematically perfect perspective.
Right.
So he drove a hook into the wall to represent the viewer's eye. He attached a long physical string to that hook. An assistant would pull the string taut, touching specific points on the physical lute. Dürer would then mark exactly where that string passed through a wooden frame, acting as his canvas.
He was performing manual analog ray tracing. He was using a physical string to simulate the linear path of light, traveling from an object to an observer's eye, capturing perfect geometry on a 2D plane. It proves that the desire to mathematically capture and project visual reality is an ancient human impulse. We just replaced the physical string with floating point math.
To truly understand how that floating point math creates a universe, we need to slow down time. We need to follow a single digital ray of light from its inception to the final coloring of a pixel on your screen. The overarching algorithm loop provided in the course structure is shockingly elegant.
It is a beautifully tight loop. It begins with the render function. For each individual pixel in the final image, the engine generates what we call a primary ray.
Okay.
It traces that ray into the 3D scene, calculates the intersection, determines the shading, returns a final color, assigns that color to the pixel, and moves to the next one.
Let's break down step 1. Ray generation. The camera has to create a ray. But how does the computer know where to point it? It starts with the 2D coordinates of the pixel on your physical monitor. Let's say we're calculating the exact center pixel of a 4K television.
The first step is translation. The engine takes those pixel coordinates and converts them into normalized device coordinates, or NDC.
NDC.
Yes, this is a mathematical normalization process that maps the entire screen space onto a grid ranging from -1 to +1.
So regardless of whether I'm on a massive IMAX screen or a tiny smartphone monitor, the bottom left corner is always coordinate 1 is 1 is 1, and the top right is always 1 anyone. It just standardizes the canvas.
Correct. Once it has that normalized coordinate, it uses the camera's specific parameters, its field of view, and its directional orientation in the 3D world to convert that flat NDC coordinate into a 3D world direction vector. The origin point of the ray is locked exactly to where the camera is positioned in the world.
Wait, I have to pause here because this brings up Empedocles and his iFire again.
Oh,
If I am understanding this workflow correctly, we are generating the ray at the camera lens, shooting it out through the virtual pixel grid, and sending it into the 3D scene. We are running physics in reverse.
you absolutely are.
In reality, a photon leaves the sun, bounces off a tree, and enters my eye. Why do we reverse engineer the universe by shooting lasers out of our virtual eyes?
It is the ultimate optimization of computational resources. Think about the behavior of a physical light source, like the sun, or even just a lamp in your living room. It is emitting countless trillions of photons every microsecond, radiating outward in a sphere. Those photons hit walls, bounce under furniture, scatter into the sky.
Right, light goes literally everywhere.
Now ask yourself, out of those trillions of photons emitted by the lamp, how many of them actually bounce off a surface and happen to perfectly strike the incredibly tiny pupil of your eye?
An infinitesimally small fraction. Practically none of them. I mean, most of the lamp's energy just warms up the wall or bounces out the window.
Exactly. If we built a rendering engine that simulated reality faithfully by shooting virtual photons out of the light sources and waiting for them to hit the camera, we would be calculating trillions of complex light paths that never contribute to the final image.
Oh, well.
We would be throwing away 99.999% of our processing power calculating photons that hit the back of a tree or fly off into the digital void.
That makes profound sense. By starting at the camera and shooting rays backward into the scene, we guarantee that every single ray we dedicate processing power to is visually important. We'll only simulate the light that actually hits the retina.
It is a brilliant inversion of physics that makes the entire discipline possible. So we have fired our primary ray out of the camera. It is a mathematical vector flying through the virtual space. Now we enter steps 2 and 3, traversal and intersection.
The algorithm needs to figure out what that ray hits first. In a basic setup, it loops through the objects in the scene. It takes our ray and tests it against the sphere, the ground plane, the wall. It uses mathematical intersection tests to ask, did a collision occur? And if so, at what distance from the camera?
And it is highly likely that a ray intersects multiple objects. It might pass straight through a transparent glass window, travel across the room, and hit a brick wall behind it.
So how does the computer know which one to actually draw?
The algorithm maintains a variable tracking the best hit. It evaluates all intersections along the ray's path and simply keeps the one with the smallest positive distance from the camera origin, the closest hit.
Because it blocks the other stuff.
Right. That is the surface the camera actually sees in that specific pixel. Everything else behind it is occluded.
And once we know exactly what object we hit, we move to step 4, shading. We fetch the material properties of that specific coordinate on the object, calculate the lighting, and determine the final color. But I don't want to just gloss over step 3, saying the computer calculates an intersection is a massive black box.
It is the math.
Yeah, how does a processor actually know that an infinitely thin, invisible mathematical line hit a virtual bubble floating in a coordinate system?
We must do the math. It is the beating heart of the entire engine. The curriculum lays out the geometry of a collision beautifully, specifically focusing on a ray-sphere intersection. It is a fantastic example because the mathematics are surprisingly elegant.
All right, we are going to dive into the algebra here, but we'll walk through it conceptually so it's not a dry textbook. We have 2 mathematical entities. First, we have the ray equation. The source material defines a ray as a function. A heat T equals O plus TDD. Let's unpack that.
The letter TD day represents any point along the ray. We are trying to find a specific point. Dollar is the origin point, where the ray starts, which we establish as our camera lens.
Right.
Dollars is the direction vector, which is essentially an arrow pointing exactly where the ray is traveling, and olives is the parameter. You can think of dollar as a time or as distance along the vector.
I found it really helpful to think of as the gas pedal in a car. If the gas pedal is at dollars, we haven't moved at all. We are sitting at the origin. If we press the pedal so dollars is dollars, we have driven exactly 1 unit of distance along our direction vector. If total is $100, we've driven 100 units.
That's exactly it.
And a crucial rule, dollar must always be greater than or equal to 0, because the ray only shoots forward out of the camera, never backward through the photographer's head.
That is a perfect visualization. The ray is a starting point, a direction, and a gas pedal. Now, we introduce our second mathematical entity, the sphere equation. A perfect sphere is defined geometrically as all points in space that satisfy a very simple rule. The distance from a point hot to the center of the sphere is exactly equal to the radius dollar.
It's just defining the surface of a bubble. If the radius is 5, then any point in the universe that is exactly 5 units away from the center coordinate is on the surface of that sphere.
Exactly. So to find the exact location where our ray pierces the sphere, we need to find a point dollars that exists on both the ray and the sphere simultaneously.
Okay, how do we do that?
We do this through algebraic substitution. We take the equation of the sphere, and everywhere it asks for a point dollars, we shove our ray equation origin plus gas pedal times direction into it.
Oh, we are mashing the two concepts together. We are asking the computer at what exact pressure on the gas pedal does the ray cross the boundary of the bubble.
Precisely. Now, to solve this algebraically, we square both sides to remove square roots associated with calculating distance. And what happens next is a moment of pure mathematical magic. When you expand that massive, messy algebraic expression, you can group the terms based on our gas pedal variable.
You end up with a structure that looks incredibly familiar to anyone who took high school algebra. You get some block of numbers multiplied by $2 plus another block of numbers multiplied by $2 plus a constant at the end, all equaling 0.
It organizes itself perfectly into standard quadratic form. $2 plus BSE plus C at BOE. The variables AO par and APO are just geometric relationships between the ray and the sphere.
Like what kind of relationships?
Well, A is based on the ray's direction. Parallel relates to how the ray is angled relative to the sphere center. And $2 is based on the starting distance.
This was a massive aha moment for me. When we talk about generating photorealistic graphics, we aren't talking about digital paint. For every single pixel on a 4K screen, which is over 8.2 million pixels, the computer is literally solving the high school quadratic formula to find a collision.
Yes. And if the game is running at 60 frames a second, it is solving that quadratic formula nearly 500 million times every single second, just for the primary rays. Solving for $2 tells the engine exactly where the collision happened. And to solve it rapidly, the computer looks at the discriminant.
That's the piece of the quadratic formula under the square root, right? 2b hood for 2.
That's the one. The discriminant is the judge. If the discriminant evaluates to a negative number, what does that mean geometrically? You can't take the square root of a negative number in real math.
In geometric terms, a negative discriminant means the ray completely missed the sphere. It flew right past it into empty space. The computer instantly knows to discard it and test the next object.
Right. And if the discriminant is exactly 0, the ray just grazed the absolute outer edge of the sphere, resulting in exactly 1 intersection point. And if the discriminant is greater than 0...
it means the ray pierced the sphere, entering through the front and exiting through the back.
Yes. This results in 2 valid values, 2 intersections. The computer uses the quadratic formula to calculate both, picks the smaller positive number because that represents the front surface facing the camera, and it finally has its exact XYZ coordinate of impact. This elegant substitution is how a blind computer mathematically feels its way through 3D space.
It is staggering to think about the scale of that computation. The computer throws out a line, churns through a quadratic equation, and definitively says, aha, I hit the surface of a sphere exactly 14.52 units away. Okay, so we've established contact. We know exactly where the surface is. Now we have to answer the most important visual question. What color is that specific point? We need to calculate the lighting.
Yes, we enter the shading phase. The material focuses on a specific, highly influential model called the full-Phong illumination model. It is a brilliant way to approximate how light interacts with surfaces. But before we even look at the material response, we have to look at the behavior of the light source itself. specifically how light decays over distance, a property known as attenuation.
Right, because a light bulb held an inch from your face is blinding, but that same light bulb viewed from a mile away is just a faint speck. The curriculum breaks down the math of attenuation into 3 layers: a constant fall-off, a linear fall-off, and a quadratic fall-off.
It uses all 3 to create a physically believable curve. The constant ensures the light doesn't become infinitely bright at 0 distance. The linear fall-off creates a steady dimming. But the quadratic fall-off is the true secret sauce.
Why is that?
In the physical world, light radiating from a point source spreads out in an expanding sphere. Because the surface area of a sphere grows exponentially, the intensity of the light drops off according to the inverse square law.
So if an object moves twice as far away from the light source, it doesn't receive half the light, it receives a quarter of the light. The energy dissipates rapidly. So we run the attenuation math, and we know exactly how much light energy is arriving at our specific intersection point.
Correct.
Now, the Phong model dictates how the material reacts to that light by breaking it into 3 pillars. The first pillar is ambient light.
Ambient light is, frankly, another cheat. In reality, light bounces endlessly. A photon leaves a lamp, hits a red rug, bounces up to hit a white ceiling, bounces down to a desk, and so on. This global illumination means that even underneath a desk, entirely blocked from the direct lamplight, it isn't pitch black. There is ambient light filling the room.
But calculating millions of endless bounces just to illuminate the dust under a desk is computationally agonizing.
Exactly. So in a basic shading model, we fake it. We add a base level of light everywhere, the ambient term. It ensures that surfaces not receiving direct light don't render as an absolute, flat, zero-value black. It acts as the mathematical floor for our lighting.
Okay, the second pillar is diffuse lighting. This represents the matte finish we talked about. And the math here relies heavily on the physical angle of the incoming light. The engine calculates the diffuse intensity by comparing 2 vectors using a dot product. Can we unpack the dot product conceptually?
Oh, definitely. Think of it as a measurement of agreement between 2 arrows. We have our surface point. We generate an arrow pointing perfectly straight out from that surface perpendicular to it. This is called the normal vector. It represents exactly which way the surface is facing.
Got it.
Then we generate a second arrow pointing from the surface directly toward the light bulb. This is the light vector.
So imagine you are holding a flat piece of cardboard, and the normal vector is an arrow glued straight up from the center. If you hold that cardboard directly under a light bulb, facing up, the normal arrow and the light arrow are pointing in the exact same direction.
And in that scenario, the dot product evaluates to a 1 part. They are in perfect agreement. The surface receives 100% maximum diffuse illumination because it is taking the light head-on. But if you tilt the cardboard, the arrows start to diverge. As the angle between them increases, the dot product shrinks. The light is hitting it at a glancing blow, spreading its energy over a larger area so the surface appears dimmer.
And if you tilt the cardboard so far that the light is actually behind it,
then the dot product yields a negative number. But we can't have negative light. That would act like a black hole sucking brightness out of the room. So the formula explicitly clamps any negative result to 0. The dot product provides that beautiful, smooth gradient of light falling across the curve of a sphere.
But what if our object isn't matte? What if it's shiny? That requires the third pillar, which is specular light.
Specular light creates the sharp, bright highlight you see on a billiard ball or an apple. Unlike diffuse light, which scatters evenly and looks the same regardless of where you stand, a specular highlight is highly directional. It depends entirely on where you, the observer, are located.
The math here involves calculating a perfect reflection vector, as if the light bounced off the surface like a laser hitting a mirror, and comparing it to the view vector, which is the path back to the camera lens.
Yes, if that reflected light ray happens to bounce perfectly down the view vector into your camera, you get hit with maximum specular intensity, a blinding white spot. The rendering engine also uses an exponent called shininess. If you apply a massive exponent to the math, it pinches the highlight, making it a tiny sharp dot like on polished metal. A smaller exponent spreads the highlight out, making it broad and soft like on a piece of plastic.
You sum up the ambient, the diffuse, and the specular, multiply it by the attenuation strength of the light source, and boom, you have the exact color value of your pixel.
Yeah.
But hold on, we are missing a massive piece of reality.
What's up?
How does the computer know if the light is even reaching the object? What if a wall is standing between our sphere and the light bulb?
Calculating shadows. To figure this out, the engine must cast an entirely new ray. This is known as a shadow ray. Once we find our surface hit point, We freeze the shading calculation. We generate a new ray originating at the hit point, aiming directly at the light source, and we throw it back into the intersection algorithm. We ask the engine, does this shadow ray hit any geometry before it reaches the distance of the light bulb?
If it does hit something, a wall, a tree, or even another part of the same object, then our original point is occluded. It is in shadow. The engine throws out the diffuse and specular calculations entirely, and the point only receives that dim baseline ambient light.
Exactly. It's a binary test for visibility. But this introduces one of the most notorious and fascinating logic bugs in computer graphics, a phenomenon known as self-shadowing.
This is an incredible gotcha moment. It stems from the fact that computers, despite their precision, cannot represent every number perfectly. We are dealing with floating point math, which eventually has to round off decimals.
Right. When the engine originally solved that quadratic formula to find the exact intersection point on the sphere, it generated an incredibly precise coordinate. But the computer's memory has limits, so it might round the last decimal place by a microscopic fraction of a millimeter.
As a result, the mathematically stored intersection point might not be exactly on the geometric surface of the sphere. The computer might round it so the point sits a billionth of an inch inside the solid mass of the sphere.
And why is that catastrophic? Because the very next step is casting the shadow ray originating from that hit point toward the light. If the origin point is mathematically submerged inside the object, the shadow ray travels zero distance before immediately colliding with the object itself.
The computer basically trips over its own shoelaces. The shadow ray fires, instantly hits the inside of its own sphere, and reports back to the engine, hey, my path to the light is blocked by the object I'm inside. The surface thinks it is in shadow, and it renders pitch black.
It creates a horrific, glitchy visual artifact known as shadow acne, where the surface covers itself in a chaotic rash of black dots as the rounding errors fluctuate across the geometry. It is a completely artificial error caused by the physical limitations of silicon memory chips trying to represent infinite real numbers.
And the fix, as the curriculum points out, is almost comically simple. It's a blatant hack.
The solution is the floating point offset. When we generate the shadow ray, we refuse to start it at the exact mathematical hit coordinate. Instead, we take the surface normal vector, that arrow pointing straight out, and we push the ray's origin point slightly outward along that arrow by a tiny factor, usually $10 to $4.
It's like we're yanking the ray slightly out of the dirt and saying, no, don't start from inside the ground, start looking from a millimeter above the ground. We artificially float the ray in midair to prevent the self-collision. It's a crude bandage over a profound mathematical limitation, but visually, it works flawlessly.
It is a perfect example of engineering pragmatism. Now, up to this point, what we have described is technically known as a raycaster. The primary ray flies out, hits a surface, shoots one shadow ray to the light, calculates the fawn color, and terminates. It creates a beautiful image, but it lacks the true magic of reality. Direct light is only half the story.
Because the real world has mirrors. The real world has water and glass. Light doesn't just hit a surface and stop. It bounces, reflects, and refracts. Upgrading from a basic raycaster to a true ray tracer requires us to tackle recursion and reflections.
If a ray hits a surface that has a reflectivity value, let's say the material is defined as a 90% perfect mirror, we cannot just calculate the direct lighting and call it a day. The direct light tells us what the mirror looks like, but we need to know what the mirror is reflecting.
To do that, the engine has to spawn another ray, a secondary or reflection ray.
The math to determine the direction of this bounce is a standard vector reflection formula. You take the incident ray, the path the light came from, and you mirror it perfectly across the surface normal vector. And crucially, we have to apply our $10 offset again, moving the origin slightly off the surface to prevent the reflection ray from colliding with its own mirror.
Floating point acne strikes again.
Ooh.
Okay, so we've calculated the perfect bounce angle. We shoot this new reflection ray out into the 3D scene. What happens next?
Here is where the architecture becomes incredibly powerful and, honestly, incredibly dangerous. The engine uses recursion. The trace function calls itself.
For anyone who isn't a software engineer, explain what a recursive function call actually does to a computer.
Imagine you were given a task. Paint a picture of a mirror. You look at the mirror, and in the reflection you see another mirror. To know what color to paint the first mirror, you have to know what is in the second mirror. So you literally pause your first task, you put it on hold, store it in your short-term memory, and begin an entirely new, identical task. Figure out the second mirror. If the second mirror reflects a red wall, you figured out the red wall, finish the second task, bring the color red back to your paused first task and say, ah, The first mirror is reflecting red.
The algorithm literally pauses its calculation of the current pixel, shoots the reflection ray, runs the entire intersection and shading algorithm from scratch for the new hit point, gets that color, and then resumes the original pixel calculation.
And it blends them. The material shows the blending equation, which strictly enforces a core law of physics: energy preservation. If the surface is a 90% mirror, the engine takes 10% of the local direct color, maybe it's a slightly dusty mirror, and blends it with 90% of the color it retrieved from the recursive bounce.
It never exceeds 100%. I mean, if you blended 50% of the local color and 90% of the reflected color, you would be mathematically creating new energy out of thin air. The object would glow brighter than the light hitting it.
Exactly. We must strictly obey the laws of thermodynamics. Light can be absorbed, it can be scattered, it can be reflected, but it cannot be miraculously multiplied by a bounce.
But I see a massive structural problem here. If the trace function calls itself, what happens when you put two mirrors facing each other? The infinite hall of mirrors effect. The primary ray hits mirror A, spawns a reflection ray to mirror B, which spawns a ray back to A, which spawns a ray to B. The computer would just freeze, endlessly stacking paused tasks in its memory until the system crashed.
It absolutely would cause a stack overflow. To prevent the engine from locking up in an infinite loop, the programmer must introduce a recursion limit or a max depth variable. The engine is artificially instructed. You are only allowed to bounce a maximum of 3 times. If a ray tries to bounce a 4th time, kill it and just return the color black.
Let me push back on that, playing devil's advocate. If I'm building a photorealistic rendering engine and 3 bounces looks good, wouldn't simulating 100 bounces look astonishingly realistic? Why cap it at 3 or 4? Isn't more physical accuracy always better?
In theory, yes. In practice, you face severe diminishing returns visually and catastrophic exponential growth computationally. Let's address the visual side first. Remember energy preservation. Every time light bounces off a surface that isn't a 100% perfect theoretical mirror, it loses energy. If light bounces off a 50% reflective surface, half its energy is absorbed. After 3 bounces, you are looking at 50% of 50%. Of 50%, only 12.5% of the original light energy remains.
It decays rapidly.
By the time a ray has bounced 10 times, its contribution to the final brightness of the pixel on your screen is so infinitesimally dark that the human eye cannot even perceive it. You are calculating microscopic variations in pitch blackness.
So it adds nothing to the image, but what does it do to the computer?
It annihilates the processor. The curriculum notes that the number of rays required per pixel grows exponentially with the depth of recursion. If every hit spawns a reflection ray and a shadow ray, and those hits spawn their own reflection and shadow rays, the math branches out like an explosive chain reaction. A scene with millions of pixels, allowing 100 bounces each. You are suddenly asking the hardware to calculate hundreds of billions of quadratic equations per frame.
Which brings us to a massive logistical question. We have all this incredibly heavy math, millions of primary rays, millions of recursive reflection bounces, calculating dot products, vector normalization, and floating point offsets. And we expect this to run 60 times a second so a video game feels smooth. How does physical hardware actually survive this onslaught of math?
It survives through a radical shift in architecture. It survives through sheer brute force parallelization. The curriculum offers a brilliant comparison between building a ray tracer on a standard CPU like writing in JavaScript versus building it on a GPU using specialized shader languages like GLSL.
Let's explore that difference. The CPU, the central processing unit, is incredibly smart and versatile. It handles your operating system, your web browser, everything, but it essentially does things sequentially. A CPU ray tracer uses nested for loops. It calculates the top left pixel, finishes it, moves to the next pixel, finishes it, and so on, marching row by row across the image. And it uses actual recursive function calls, pausing and stacking memory.
The CPU is like a single brilliant mathematician sitting at a desk.
Yeah.
Give them a complex equation and they will solve it flawlessly. But if you ask them to solve 8 million quadratic equations in 16 milliseconds, they will fail. The GPU, the graphics processing unit, is fundamentally different. It is not one brilliant mathematician. It is a stadium filled with 10,000 moderately smart mathematicians, all instructed to work at the exact same time.
Massive parallel processing. The GPU doesn't do pixel 1, then pixel 2. It calculates thousands of pixels simultaneously. The material explains that in GLSL, the entire 3D universe, the arrays of spheres, the lists of lights, the material properties, is uploaded directly into the memory of the graphics card as uniform structures.
And here is the profound architectural shift. Standard GPUs are notoriously bad at handling deep recursion. Their memory architecture is built for speed and throughput, not for pausing and stacking thousands of complex, nested function calls. If you force a stadium of mathematicians to keep pausing their work to ask each other questions, the whole system bottlenecks in what's called thread divergence.
So if the hardware hates recursion, how do we bounce the light?
We cheat the software to match the hardware. Instead of a function calling itself, the GPU shader uses an iterative loop to simulate recursion. It uses a standard for loop that is hard-coded to run, say, 3 times. Inside that loop, it traces the ray, finds the hit, adds the direct light, calculates the new reflection vector, overwrites the old ray with the new ray, and simply loops again. It unrolls the recursion into a flat, predictable iteration.
It is brilliant, and the shader applies this logic to the screen using a technique called a full-screen quad. You aren't actually drawing the 3D shapes. You literally just draw 2 massive triangles that cover your entire 2D monitor, turning your screen into a flat canvas. Then the GPU fires up its stadium of mathematicians and runs this iterative physics simulation for every single pixel on those 2 flat triangles simultaneously.
You are turning a completely flat geometric plane into a mathematical window looking into a simulated universe. It is the ultimate magic trick of modern hardware design. It is the reason real-time ray tracing, which was considered an impossible holy grail just 10 or 15 years ago, is now running on consumer consoles in living rooms. We have forged silicon chips specifically optimized to trace billions of intersecting vectors in parallel.
It really is a marvel. But as we wrap up, I want to pivot slightly, because it's not just about pretty graphics, is it? We've spent this entire time talking about photorealistic oceans, shiny blue spheres, and cinematic shadows. But the fundamental math of shooting a mathematical line through 3D space to see what it hits has profound implications far outside of Hollywood visual effects and gaming.
Absolutely. At its absolute core, a raycaster is just a spatial query. The algorithm is asking the universe 2 very simple questions. Is there a geometric boundary along this specific vector? And if so, exactly how far away is it? That is a question with immense utility in countless scientific and engineering fields.
The curriculum lists several non-graphical uses. Let's talk about visibility computation. If you have ever played a stealth video game and an enemy guard spots you hiding behind a crate from across a courtyard, that wasn't arbitrary game logic. The game engine literally cast an invisible, unrendered ray from the center of the guard's 3D head directly towards your character's 3D body.
Exactly. The engine performed the exact same ray primitive intersection test we spent the last hour dissecting. If the ray hit the crate's geometry first, the algorithm returned a closer distance for the crate and for the player. The guard's line of sight was mathematically occluded. If you stepped out, the ray hit your character first, the distance checked out, and the alarm triggered. Line of sight artificial intelligence is literally just ray casting with the shading module turned off.
The sources also mention physics engines and collision detection. When a digital car crashes into a digital wall at 100 miles an hour, the engine is rapidly casting short rays from the car's bumper along its velocity vector to see if those rays intersect the wall's geometry before the next frame is drawn. If there is a hit, the physics engine takes over and crumbles the bumper.
It expands far beyond software, too. Consider acoustic engineering. How does an architect know what a new symphony hall will sound like before they pour the concrete? Sound waves behave remarkably similarly to light waves in terms of bouncing and attenuation. Engineers use ray tracing to simulate audio. They cast millions of acoustic rays from the stage, calculate the reflections off the walls, measure the absorption properties of the velvet seats, and simulate exactly what a cello will sound like in seat 14B.
That is wild. You can literally hear a room that doesn't exist yet because of a geometric intersection algorithm. And finally, radar. Radar is literally real-world analog ray casting. A dish shoots a physical electromagnetic wave out into the sky, waits for it to bounce off the metallic surface of an airplane, and measures the microsecond delay of the return bounce to calculate distance. Our digital ray tracer is just the virtual simulation of that exact physical reality.
It demonstrates just how fundamental this specific branch of geometry is to understanding the physical world. The mathematical intersection of a line and a surface dictates almost everything about how we perceive space, whether we are processing it visually through our eyes, acoustically through our ears, or physically through a radar dish.
We have covered a massive amount of ground today. Let's briefly recap this incredible journey. We started with an empty, infinite void, our Math 3 and coordinate space. We populated it with mathematical primitives, carved them with Boolean logic, and clothed them in materials of diffuse matte and specular shine. We place a virtual camera to act as our observer.
We then explored the limitations of the fast but fake rasterization process, understanding why it ultimately fails to capture the true optical complexity of reality. We embraced the computationally terrifying but physically accurate realm of ray tracing, armed with its logarithmic NN scalability.
We followed a primary ray backward out of the camera, optimizing our processing power. We used high school algebra to substitute a line equation into a sphere equation, solving the quadratic formula to pinpoint the exact microscopic moment of collision. We calculated the inverse square decay of light.
We offset our shadow rays by a microscopic $10 to avoid the dreaded self-shadowing acne, ensuring the computer didn't trip over its own rounding errors. And then we let the rays bounce, simulating the infinite hall of mirrors using iterative loops deployed across stadiums of parallel GPU cores, strictly obeying the laws of thermodynamic energy preservation.
It is an astonishing stack of human ingenuity. We took the messy, infinitely complex analog reality of light, simplified it into elegant algebraic equations that preserve energy and respect spatial geometry, and fed it into silicon chips that can run those calculations hundreds of millions of times a second.
It is a triumph of applying mathematical abstraction to replicate physical phenomena.
Which leads me to a final, somewhat mind-bending thought to leave you with. The next time you are playing a game or watching a movie and you stop to admire a puddle reflecting a flickering neon sign, take a moment to realize what you are actually seeing. You aren't just looking at digital art. You are looking at millions of quadratic equations, floating point offsets, and strict thermodynamic physics simulations, firing in perfect parallel unison every 60th of a second. It is a flawless mathematical illusion. But it makes you wonder, if our computers, built by human hands out of melted sand, can simulate the physics of light this convincingly by just doing math really, really fast, what does that say about the physics of our own universe? If light fundamentally behaves like a computational algorithm resolving intersections in a coordinate space, could reality itself just be a massive computational system? The next time you look in a real mirror, ask yourself, are you seeing a physical reflection, or are you just living inside a very, very efficient dollar rendering engine?
Now there's a thought to keep you up at night. Until next time, keep exploring the math behind the magic.